This is beginning section 9 of chapter 30. It's lecture 27 from Monday the 6th of April. This section is going to cover LC circuits. So those are circuits that have inductors and capacitors in them. That's pages 861 to 863 from your textbook. These are pretty important circuit elements. We're going to start with the idea, kind of a qualitative look, of what happens to the current, and we'll discuss what happens to the energy. Then we'll talk about some applications, then we'll do the equations and some examples. So we begin by connecting a fully charged capacitor to an inductor in a circuit with an open switch. We close the switch and then we ask what happens. Well, if there were no inductor, the current would just start to flow normally, and then the capacitor would eventually discharge. But that can't happen this time because the inductor is present in the circuit. The current wants to flow, but the inductor opposes that change. So we have two competing things going on there. So at every instant, the potential across the capacitor is equal to the potential across the inductor. And the potential across the inductor is minus the inductance times the rate of change in current. So the current is going to increase when we close the switch. The current wants to turn on. But the rate of change of current is going to decrease. So it will increase, but it will increase more slowly as it goes. Right at the very beginning, all of the energy is stored in the electric field of the capacitor. So that's right at the beginning as soon as the switch closes. So then what happens a little while later, eventually the rate of change of current is going to go to zero because it was decreasing. The rate of change was decreasing as the potential decreased. When the rate of change of current gets to zero, then the potential across the inductor is zero because the potential depends on the rate of change of current. If the potential across the inductor is zero, then the potential across the capacitor is zero. So what does this mean? If the current was increasing and the rate of change is now zero, must mean we got to a maximum current. So that's one thing. We must have hit the maximum. If the potential is zero, then there must be no charge on the capacitor. So when the current is a maximum, the capacitor is fully discharged. In a normal circuit without an inductor, it would mean that there would be no more current flow. But of course, this can't be possible because there is an inductor and it doesn't want it to go straight to zero. It's going to oppose that change. So before we talk about that change, we'll just talk about the energy. Also, if the capacitor is fully discharged, it means there's no charge on the plates, so there's no electric field between the plates, so there's no energy stored in the electric field. Where did the energy go? Well, now it's stored in the magnetic field of the inductor. So that's what happens at the end of this cycle. So next, even though our capacitor was now fully discharged, the current can't go to zero right away because of the inductor. So the current starts to decrease because it's trying to get to zero. The inductor opposes the decrease and will induce current in the same direction. So that's going to be a current in the opposite direction of what it was before. That current is going to flow until the capacitor is fully charged again. But now, because the current is flowing in the opposite direction, the polarity of the plates are going to switch. So the plate that was negative before is now positive, and the plate that was positive before is now negative. Once the capacitor is fully charged, now all of the energy is back into the electric field. So now where are we? Now we're in a place where the capacitor is fully charged, and it's going to begin to discharge again, just like it did before. Except the current is going to flow in the opposite direction because of the opposite polarity of the plates. That's going to keep happening until the capacitor is discharged, the current is a maximum, and all of the energy is stored into the magnetic field, and so on. That process is going to keep repeating. The capacitor will be charged, it will discharge, and then it will recharge over and over again, all the while switching polarity. So then the applications of this is in telecommunication. Super important right now. Everybody is telecommuting, working from home, and depending more and more on their phones and computers and all of those things. So what happens is all of the telecommunication devices, they all depend on electromagnetic signals. And they all depend on the signals, which oscillate with a well-defined frequency. And we're going to get into the details of that dependence when we go through the math. So if you want something with a well-defined frequency, you can generate that with this kind of circuit because the signal oscillates back and forth in direction. So the next thing we're going to do is go through the math to see the equations, how it all works, and then we'll do some examples.